In 1977, humanity launched 2 spacecraft that would become the farthest-traveling objects ever built. Voyager 1 and Voyager 2 crossed the entire outer solar system, revealed worlds no one had ever seen up close, and eventually pierced the boundary of interstellar space itself. They are still out there right now, more than 15 billion miles from home, whispering data back to Earth on the power of a refrigerator light bulb. These missions changed everything we knew about the cosmos. And yet, in the nearly 5 decades since they launched, we never sent a third, not a successor, not an upgrade, not even a spiritual follow-up built in the same bold tradition. The question almost nobody asks is the one that matters most. Why not? If you enjoy deep dives into the stories behind humanity's greatest missions, and you want to understand why some of our boldest moments in space were never repeated, do me a favor and tap that like and subscribe button. I appreciate every one of you that supports the channel. Now, with all that being said, settle in and get yourself comfortable. Let's begin. The most important discovery in the history of interplanetary exploration began with a pencil, a sheet of graph paper, and a young graduate student who had no idea what he was about to find. In 1964, Gary Flandreau was working part-time at NASA's Jet Propulsion Laboratory in Pasadena, California. He was an aeronautics student, not yet a full engineer, and his assignment was simple enough on paper: plot the future positions of the outer planets and see whether any interesting mission opportunities existed beyond Mars. Nobody expected much. The outer solar system was considered a wasteland of distance and cold. Jupiter alone sat nearly 400 million miles from Earth at its closest approach. Saturn was twice as far. Uranus and Neptune were so remote that most scientists considered them effectively unreachable within a single human career, let alone a single mission. Flandreau began charting planetary positions year by year, penciling the orbital tracks of Jupiter, Saturn, then to Uranus and Neptune across decades of future time. What he saw stopped him cold. In the late 1970s, all 4 giant planets would line up on the same side of the Sun in a loose arc, a configuration so rare it occurs only once every 175 years. The previous alignment had taken place around 1801, when Thomas Jefferson was president and the steam locomotive had not yet been invented. The next one would not come again until roughly 2153, but the alignment was more than a celestial curiosity. Flandreau realized that a spacecraft launched during this window could use each planet's gravity to bend its trajectory and accelerate toward the next. Like a ball bouncing off a series of moving walls, each bounce adding speed and redirecting the path. This technique, called gravity assist, meant that a single probe could visit Jupiter, then slingshot to Saturn, then to Uranus, then to Neptune, completing a grand tour of the outer solar system in about 12 years. Without the alignment, a direct mission to Neptune alone would require over 30 years of flight time. With it, you could see 4 planets for the fuel cost of reaching one. Flandreau brought his findings to his supervisors. Some of them told him it was impossible. Stop wasting their time. The engineering challenges were absurd. No spacecraft had ever functioned for more than a few years in deep space. No probe had ever navigated complex gravitational encounters at distances where radio signals took hours to travel each way. No one had ever attempted a gravity assist at all, let alone 4 of them in sequence. The concept required a spacecraft smart enough to manage itself across a journey longer than any machine had ever survived, through radiation environments that would cook unshielded electronics, past moons and ring systems whose properties were almost entirely unknown. But the math was undeniable, and the clock was ticking. If NASA wanted to exploit this alignment, the launch window would open in 1977 and close within months. Miss it, and the opportunity would vanish for nearly 2 centuries. By 1966, JPL was actively promoting what it called the Grand Tour. The original vision was ambitious even by the standards of the Apollo era. NASA planned to build 4 identical spacecraft, 2 to launch in 1977 on trajectories visiting Jupiter, Saturn and Pluto, and 2 more to launch in 1979 toward Jupiter, Uranus, and Neptune. These would be large, heavily instrumented probes called thermoelectric outer planet spacecraft, or TOPS, designed from the ground up for missions lasting a decade or more. The scientific community was ecstatic. For the first time, humanity could survey every giant planet in a single coordinated campaign. Then the budget collapsed. The story of how Voyager almost never happened is the first clue to understanding why Voyager 3 never did. By the early 1970s, NASA's golden age was ending. The Apollo program had consumed the better part of a decade and commanded over 4% of the entire federal budget at its peak in 1966. That kind of spending had been driven by Cold War urgency, a national mandate to beat the Soviet Union to the moon. Once Apollo 11 landed in 1969, the political fuel that had powered NASA's budget evaporated almost overnight. The Nixon administration slashed funding aggressively. Apollo missions 18, 19, and 20 were cancelled. The agency's workforce shrank. Budgets fell year after year in real terms. In this contracting environment, NASA faced an agonizing choice. The agency needed a major human spaceflight program to sustain its workforce and institutional identity after Apollo. The answer was the Space Shuttle, a reusable orbiter that promised routine, affordable access to low Earth orbit. The shuttle was approved in January 1972. It would dominate NASA's budget, its engineering talent, and its political attention for the next 4 decades. Something had to give. And what gave, in December 1971, was the Grand Tour. NASA headquarters cancelled the 4 spacecraft Outer Planets program. The cost was too high, the risk was too uncertain, and the shuttle needed the money. The planetary science community was devastated. An entire generation of scientists saw the most ambitious solar system exploration campaign ever conceived killed before a single spacecraft was built. One NASA official would later describe the cancellation as a direct trade. The Grand Tour died so the shuttle could live, but JPL did not give up. Engineers at the laboratory proposed a stripped-down alternative, a mission using only 2 spacecraft based on the existing Mariner platform, targeting just Jupiter and Saturn instead of all 4 outer planets. The mission was called Mariner Jupiter-Saturn, or MJS-77. It was approved in May 1972, barely 5 months after the Grand Tour was killed. The 2 probes would be cheaper, simpler, and designed for a primary mission lasting just 4 years. There was no official commitment to visit Uranus or Neptune. Officially, those destinations did not exist in the mission plan, but the engineers at JPL had a quiet understanding among themselves. They would build these spacecraft to last longer than 4 years. They would design trajectories that kept the option open. They would construct hardware tough enough to survive a journey the bureaucrats had not authorized. If both probes succeeded at Jupiter and Saturn, and if the spacecraft were still healthy, NASA could decide later whether to extend the mission onward. It was a calculated institutional gamble. Build for the minimum, hope for the maximum, and do not tell Congress you are planning a 12-year mission when you only have approval for 4. In March 1977, just months before launch, NASA held a public competition to rename the mission. The winning entry was Voyager, a name that had originally been proposed years earlier for a different Mars mission that was also cancelled. The 2 spacecraft were redesignated Voyager 1 and Voyager 2. Voyager 2 launched first, on August 20th, 1977, aboard a T-tangent Centaur rocket from Cape Canaveral. Voyager 1 followed on September 5th, on a faster, shorter trajectory designed to reach Jupiter and Saturn sooner. Despite launching second, Voyager 1 would arrive at Jupiter 4 months ahead of its twin. Each spacecraft weighed roughly 1,800 pounds. Each carried a suite of 10 scientific instruments, including cameras, spectrometers, magnetometers, and particle detectors. Each was powered by 3 radioisotope thermoelectric generators, devices that converted the heat from decaying plutonium-238 into electricity. There were no solar panels. At Jupiter's distance, sunlight is 25 times weaker than at Earth. At Neptune, it is 900 times weaker. Solar power was useless. The plutonium generators would provide roughly 470 watts at launch, declining by about 4 watts per year as the plutonium slowly decayed. The computers on board each Voyager were extraordinary for their time and laughable by modern standards. The total memory across all 6 computers on each spacecraft amounted to roughly 68 kilobytes. A modern smartphone carries millions of times more processing power. The cameras used analog television technology similar to what was broadcasting primetime sitcoms back on Earth. The entire electronic complexity of each Voyager was equivalent to roughly 2,000 color television sets. Yet these machines were designed with something more valuable than raw computing power. They carried fault protection software that allowed them to detect problems and switch to backup systems autonomously, without waiting hours for instructions from Earth. This capability had never been built into a deep space probe before. It was essential because at Jupiter, a round-trip radio signal took nearly 100 minutes. At Neptune, it would take over 8 hours. If something went wrong, the spacecraft had to save itself. Voyager 1 reached Jupiter in March 1979. What it found there rewrote planetary science overnight. The Great Red Spot, long observed as a mysterious oval in telescopic images, revealed itself as a colossal anticyclonic storm large enough to swallow 2 or 3 Earths, with wind speeds exceeding 400 miles per hour at its edges. Jupiter's atmosphere showed turbulent bands, swirling vortices, and lightning strikes more powerful than any ever recorded on Earth. But the real shocks came from the moons. Io, the innermost of the 4 large Galilean satellites, was supposed to be a dead, cratered world. Instead, Voyager 1 captured images of active volcanic eruptions, towering plumes of sulfur and sulfur dioxide blasting hundreds of miles above the surface. Io was the most volcanically active body in the entire solar system, its interior heated not by radioactive decay like Earth's, but by the relentless gravitational kneading of Jupiter's immense tidal forces. No one had predicted this. The discovery was made by navigation engineer Linda Morabito, who noticed the volcanic plume in a routine navigation image. It was one of the most stunning surprises in the history of space exploration. Europa, another of Jupiter's large moons, presented a surface unlike anything scientists had seen. Smooth, bright, and crisscrossed with dark fractures, it looked like a cracked eggshell. The fractures suggested that the icy surface was shifting and renewing itself, hinting that liquid water might exist beneath the frozen crust. This single observation planted the seed for what would become one of the most profound questions in planetary science. Could there be a habitable ocean hidden inside a frozen moon, orbiting a gas giant nearly 500 million miles from the Sun? Voyager 1 then continued to Saturn, arriving in November 1980. Its trajectory was optimized for a close flyby of Titan, Saturn's largest moon, which was known to possess a thick, nitrogen-rich atmosphere denser than Earth's. The Titan encounter was considered so scientifically important that NASA was willing to sacrifice the rest of Voyager 1's planetary mission to get it. The close approach bent Voyager 1's trajectory sharply northward, out of the plane where the planets orbit, ending any possibility of continuing to Uranus or Neptune. Voyager 1's planetary tour was over. It had visited 2 planets and would now begin a long, lonely cruise toward the stars. But Titan delivered. Voyager 1's instruments revealed an atmosphere composed primarily of nitrogen with significant amounts of methane and other hydrocarbons. The surface was completely hidden beneath an opaque orange haze. Temperature and pressure measurements suggested that conditions near the surface might allow methane to exist as a liquid. Titan might have lakes, rivers, and rain made not of water, but of liquid natural gas. It would take another 25 years and the Cassini-Huygens mission to confirm these suspicions, but Voyager provided the first evidence. Saturn's rings proved far more complex than anyone had imagined. Ground-based telescopes had revealed a handful of broad ring divisions. Voyager's cameras showed thousands of individual ringlets, braided structures, gaps maintained by tiny shepherd moons, and spoke-like features rotating across the ring plane that defied easy explanation. The ring system was not a simple static structure. It was dynamic, intricate, and governed by gravitational interactions so subtle that theorists would spend decades modelling them. Now everything depended on Voyager 2. Because Voyager 1 had been diverted to Titan, only Voyager 2 retained the trajectory needed to continue the grand tour to Uranus and Neptune. If Voyager 2 failed at Saturn, the grand tour would die. Humanity would not see Uranus or Neptune up close for generations. Voyager 2 reached Saturn in August 1981 and performed its flyby flawlessly. The spacecraft's camera platform briefly jammed during the encounter, a terrifying malfunction that engineers managed to resolve by switching to a slower scan rate. With Saturn behind it, Voyager 2 was now committed. Its trajectory bent toward Uranus, 5.5 years away. No one at NASA had officially planned this far. The spacecraft was already beyond its 4-year design life. Every additional month of operation was borrowed time. Voyager 2 arrived at Uranus in January 1986, becoming the first and still the only spacecraft to visit the 7th planet. What it found was genuinely alien. Uranus orbits the Sun tipped almost completely on its side, rolling along its orbital path like a ball rather than spinning upright like the other planets. Its magnetic field was tilted 60 degrees from its rotational axis and offset from the planet's center, a configuration so bizarre that no existing model could explain it. The atmosphere appeared nearly featureless in visible light, a pale blue-green sphere with almost no cloud activity. But infrared and ultraviolet observations revealed subtle banding and a surprisingly active upper atmosphere. Voyager 2 discovered 10 previously unknown moons and 2 new rings, bringing the total known ring count to 11. The spacecraft then turned toward Neptune, 3.5 more years of flight through increasingly empty space. The light levels at Neptune were so dim that the camera exposure times had to be extended dramatically. Engineers reprogrammed the spacecraft's aging computers from Earth, uploading new software across billions of miles to compensate for the faint illumination. The fact that they could upgrade a spacecraft's operating system from that distance using 1970s hardware remains one of the most underappreciated engineering achievements of the 20th century. Voyager 2 reached Neptune in August 1989, 12 years after launch. The encounter was everything scientists had hoped for and more. Neptune's atmosphere raged with the fastest winds ever measured on any planet, exceeding 1,200 miles per hour. A massive storm system called the Great Dark Spot dominated the southern hemisphere. The planet's moon, Triton, long suspected of being a captured Kuiper Belt object, revealed active geysers of nitrogen gas erupting from its frozen surface, making it one of the few geologically active worlds in the outer solar system. Triton's surface temperature measured -391 degrees Fahrenheit, the coldest surface ever recorded on a solid body in the solar system. With Neptune behind it, Voyager 2's planetary mission was complete. Both spacecraft had now exceeded every expectation. They were designed to last 5 years. They had operated for 12. They were built to visit 2 planets. Together they had explored 4, along with dozens of moons and ring systems. The total cost of the Voyager program, from approval through the Neptune encounter, including both spacecraft, their launch vehicles, their radioisotope power sources, and all deep space network tracking support, was $865 million. In today's currency, that is roughly $3.5 billion. For that price, humanity received its first comprehensive survey of the outer solar system. No scientific mission before or since has delivered a comparable volume of discovery per dollar spent. But the missions did not end at Neptune. In 1990, NASA extended both spacecraft under the Voyager Interstellar mission with a new objective: reach and characterize the boundary where the Sun's influence ends and interstellar space begins. Both probes continued outward, growing fainter, losing power year by year, instrument by instrument, but never fully dying. On August 25, 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to the interstellar medium. It became the first human-made object to enter the space between the stars. Voyager 2 followed on November 5, 2018. Nearly half a century after launch, both spacecraft were still transmitting data from regions of space that no instrument had ever sampled. They were measuring magnetic fields, plasma densities, and cosmic ray fluxes in a place that existed only as theory before they arrived. The Voyager program did something no other space mission has done. It started as a compromise, a stripped-down substitute for a grander vision that was killed by budget politics. It was approved for 4 years and lasted nearly 50. It was designed for 2 planets and explored 4. It was built with 68 kilobytes of memory and navigated the most complex series of gravitational encounters ever attempted. Every single major discovery it made was a surprise. Active volcanoes on Io, a possible ocean on Europa, hydrocarbon rain on Titan, supersonic winds on Neptune, nitrogen geysers on Triton, rings, moons, magnetic fields, and atmospheric phenomena that no one had predicted. The twin Voyagers did not just meet expectations. They invented expectations that did not exist before they arrived. But Voyager did not become iconic purely because of what it discovered. It became iconic because of who told the story. Carl Sagan, the astronomer and science communicator who served on the Voyager imaging team, understood something that most scientists did not. He understood that a space mission is not just a data collection exercise, it is a narrative. And narratives need a voice. Sagan became that voice. Through his television series Cosmos, his best-selling books, and his tireless public advocacy, he transformed Voyager from a NASA project into a human story. He was the one who championed the idea of turning Voyager 1's camera back toward Earth from nearly 4 billion miles away to capture the pale blue dot photograph, an image that had no scientific value whatsoever, but became one of the most emotionally powerful photographs ever taken. He chaired the committee that designed the golden records, those golden discs encoded with music, images, and greetings from Earth, attached to each spacecraft as messages to any intelligence that might someday find them drifting between the stars. The records were Sagan's idea. They were his insistence that a scientific mission should also carry meaning, that exploration was not just about instruments and data, but about who we are and what we value. Sagan gave Voyager a soul. He made the public care about 2 machines flying through the darkness of the outer solar system, not just because the science was interesting, but because the journey itself was beautiful. He framed Voyager as an expression of humanity's best instincts, the curiosity, the courage, the willingness to send a piece of ourselves into the unknown with no guarantee of return. That framing lodged Voyager permanently in the cultural imagination in a way that no purely scientific achievement could have accomplished alone. And it is precisely that cultural resonance that makes the absence of a successor so difficult to explain. And this is precisely why the absence of a follow-up feels so baffling. Think about it from the perspective of someone who lived through those decades of discovery. You watched 2 spacecraft transform the outer solar system from a collection of dim dots into a gallery of vivid, complex worlds. You saw NASA demonstrate that long-duration, multi-planet missions were not only possible but spectacularly productive. You watched the engineering teams prove that spacecraft could survive far longer than their warranties, navigate challenges no one had anticipated, and return science that reshaped entire fields of study. Everything about the Voyager experience suggested that this was a beginning, a proof of concept for something bigger, something bolder, something that would naturally follow as technology improved and budgets recovered. The assumption was obvious. If Voyager 1 and Voyager 2 could accomplish all of this with 1970s technology, surely a Voyager 3 would come along with better instruments, faster processors, more capable communications, and an even more ambitious mission profile. Maybe it would carry a nuclear electric propulsion system to reach the outer planets faster. Maybe it would deploy atmospheric entry probes into the ice giants. Maybe it would be the first spacecraft specifically designed from the start to cross into interstellar space and study what lies beyond the sun's domain. The public waited. Scientists proposed. Engineers drafted concepts. Decades passed. And nothing launched. No Voyager 3. No spiritual successor. No deep space flagship built in the same exploratory tradition. the most successful interplanetary mission in human history, produced no direct follow-up. The spacecraft that proved long-range exploration was possible received no air. The question seems simple enough. If it worked so well, why did nobody do it again? But the answer runs deeper than budget spreadsheets and mission timelines. It reaches into the structure of how space agencies make decisions, how political priorities shift across generations, and how the very conditions that made Voyager possible were far more fragile and temporary than the public ever understood. What comes next reveals exactly how those conditions disappeared, and why getting them back has proven so much harder than anyone imagined. To understand why Voyager 3 never happened, you first have to understand something uncomfortable about why Voyager 1 and 2 happened at all. They were not the product of a system designed to produce bold exploration. They were the product of a fluke, a convergence of circumstances so specific and so temporary that once those circumstances passed, the kind of mission Voyager represented became almost structurally impossible to repeat. Start with the planets themselves. The alignment that Gary Flandreau discovered in 1964 was not merely convenient, it was the single enabling condition for everything that followed. Without it, the entire concept of a multi-planet flyby mission to the outer solar system collapses. The physics is unforgiving. Jupiter orbits the Sun once every 12 years. Saturn takes 29 years. Uranus requires 84. Neptune takes 165. These orbital periods mean that the four giant planets spend the vast majority of their time scattered across different quadrants of the solar system, separated by billions of miles of empty space, with no efficient route connecting them. But roughly once every 175 years, the orbital arithmetic produces a brief window in which all four giants line up on the same side of the Sun in a configuration that allows gravity-assist trajectories from one to the next. The spacecraft does not carry enough fuel to fly directly to each planet. Instead, it falls into the gravitational field of the first planet, uses that planet's orbital momentum to gain speed and redirect its course, then coasts to the next planet and repeats the maneuver. Each gravity assist is essentially a free course correction and speed boost donated by the planet's own motion around the Sun. Without these assists, a mission to Neptune would require either a vastly more powerful rocket, a vastly longer flight time, or both. Consider the numbers. Voyager 2 reached Neptune in 12 years using gravity assists from Jupiter, Saturn, and Uranus. A spacecraft launched directly to Neptune without gravity assists would need roughly 30 years to arrive, assuming the same propulsion technology. That is not a mission any space agency can easily justify. 30 years spans multiple presidential administrations, multiple congressional funding cycles, multiple generations of engineers and scientists. The people who designed the spacecraft might retire or die before it reaches its destination. The institutional memory required to operate it would have to survive 3 decades of personnel turnover, budget battles, and shifting priorities. 12 years is already an extraordinary commitment by the standards of government-funded science. 30 years is nearly impossible. This is why the alignment mattered so much. It compressed a multi-decade odyssey into a single career-length mission. It made the impossible merely very difficult, and it created a deadline. The launch window opened in the summer of 1977. It would remain viable for only a few months. Miss it, and the next comparable opportunity would not arrive until the middle of the 22nd century. Every human being alive in 1977 would be long dead before the planets aligned again. NASA made the window. Barely. The spacecraft launched on time, the gravity assists worked. The Grand Tour succeeded beyond anyone's reasonable expectations. But here is the critical point that most people miss when they ask why there was no Voyager 3. The planetary alignment did not just make Voyager possible, it made Voyager necessary. The urgency of the alignment is what drove the funding, the engineering, the institutional will, and the political tolerance for risk. Without that ticking clock, without the knowledge that this chance would not come again for 175 years, It is genuinely unclear whether the mission would have survived the budget cuts that killed the original Grand Tour in 1971. The alignment created a now or never pressure that overrode the normal bureaucratic inertia of a shrinking agency. Once the window closed, that pressure vanished, and nothing equivalent has replaced it. The planets are not aligned today. They will not be aligned tomorrow. There is no comparable multi-planet gravity assist opportunity available in the current century that replicates what Voyager had. Individual missions to individual outer planets remain possible, and several have been proposed. But a single spacecraft visiting all 4 giant planets in sequence, the architecture that defined Voyager's identity and captured the public imagination, cannot be replicated until the geometry returns. The window did not just close, it locked. Now layer the political and financial reality on top of the astronomical one. When NASA approved the Mariner Jupiter-Saturn mission in May 1972, the agency was already in steep decline. The Apollo program had consumed an astonishing share of national resources. At its peak in 1966, NASA's budget represented 4.41% of all federal spending. That is a number worth pausing over. Imagine the United States government deciding that more than 4 cents of every dollar it spent should go to a single civilian agency dedicated to space exploration. That level of investment was driven entirely by the Cold War. The Soviet Union had launched Sputnik in 1957. Yuri Gagarin had orbited Earth in 1961. President Kennedy had responded with a national mandate to reach the moon before the decade was out. The money followed the mandate. NASA's workforce swelled to over 34,000 employees, supported by 375,000 contractors across industry and academia. It was a wartime mobilization aimed at the heavens rather than a battlefield. Then Apollo 11 landed. The mandate was fulfilled. The political fuel that had driven the spending evaporated almost immediately. The Nixon administration viewed NASA's budget as an easy target for cuts. Apollo missions were cancelled. Budgets shrank year after year. By 1975, NASA's share of federal spending had fallen below 1%. By 1986, it had dropped to 0.75%. It has never returned to anything close to the Apollo-era peak. In the decades since, NASA has averaged roughly 0.7% of annual federal spending, and more recently has fallen below 0.4%. The difference between 4% and less than 1% is not a rounding error. It represents a fundamental transformation in how the United States prioritizes space exploration relative to every other demand on the national treasury. Within this shrinking overall budget, the competition for resources became ferocious, and the single largest competitor for NASA's internal funding was not a science mission. It was the Space Shuttle. The shuttle was approved in January 1972, less than a month after the Grand Tour was cancelled. This is not a coincidence. The agency could not afford both. The shuttle was pitched as a revolution in spaceflight, a reusable vehicle that would make access to low Earth orbit routine and affordable. It would launch satellites, service space stations, carry scientific experiments, and support national security payloads. Its projected per-flight cost was supposed to be dramatically lower than expendable rockets. The shuttle was NASA's lifeline, the program that would justify the agency's continued existence in the post-Apollo era, maintain its workforce, and sustain the political support of congressional districts where aerospace contractors employed thousands of voters. The reality fell catastrophically short of the promise. The shuttle never achieved routine or affordable operations. Its development costs ballooned. Its per-flight cost, originally projected at roughly $20 million, averaged closer to $450 million per mission in inflation-adjusted terms over the program's lifetime. The total program cost from inception through retirement in 2011 reached approximately $209 billion in 2010 adjusted figures. The shuttle consumed between 30 and 40% of NASA's annual appropriations throughout the 1980s and 90s. This was money that could not be spent on planetary exploration, on astrophysics, on Earth science, or on developing next-generation propulsion systems that might have enabled a Voyager successor. the effect on planetary science was devastating. Between 1978, when Pioneer Venus launched, and 1989, when Galileo finally left Earth aboard the Space Shuttle Atlantis, NASA did not launch a single new planetary exploration mission. 11 years. An entire decade in which the only data arriving from the outer solar system came from Voyager 1 and Voyager 2, spacecraft that were already in flight before the drought began. Historians of space science call this period the lost decade of planetary exploration. It was not lost because scientists stopped having ideas. It was lost because the money was going elsewhere. The shuttle's impact extended beyond simple budget competition. NASA had decided in the late 1970s that the shuttle would be the primary launch vehicle for all major payloads, including planetary probes. This decision forced mission designers to build their spacecraft around the shuttle's specifications and schedule. Galileo, the Jupiter orbiter originally expected to reach the outer solar system in the mid-1980s, was delayed repeatedly by the shuttle program's scheduling constraints and then grounded entirely by the Challenger disaster. It would not leave Earth until 1989 and would not reach Jupiter until 1995. A mission conceived in the same year the Voyagers launched took nearly 2 decades to arrive at its destination. A mission that could have been operating at Jupiter in the early 1980s was delayed until the mid-1990s, primarily because of institutional decisions that had nothing to do with planetary science. The Ulysses solar mission was delayed by 4 years. Mars Observer, an orbital mission to the Red Planet, was pushed back by 2 years and then lost entirely just before orbit insertion in 1993, most likely due to a catastrophic fuel system rupture. The drought in planetary launches was not caused by a shortage of good mission concepts or qualified scientists or capable engineers. It was caused by an agency that had bet its institutional future on a single transportation system that absorbed most of its budget, monopolized its launch capacity, and then spectacularly failed, taking the entire launch manifest down with it. Consider what this meant for anyone hoping to build a Voyager successor during the 1980s. First, the planetary alignment that had enabled the original Grand Tour was gone. No comparable opportunity existed. Second, NASA's overall budget had contracted by a factor of 4 or 5 relative to the Apollo peak. Third, the space shuttle was consuming the largest share of what remained. Fourth, the shuttle disaster had grounded all launches for years and eliminated the most capable upper stage option for reaching the outer planets. Fifth, the political appetite for expensive, high-risk exploration missions had cratered along with public confidence in NASA's ability to manage complex programs safely. Any proposal for a Voyager-class deep space flagship during this period would have had to compete for funding against the shuttle's ongoing operational costs, against the planned space station Freedom that would eventually become the International Space Station, and against a growing backlog of delayed missions that had been waiting for launch opportunities since before the Challenger accident. The proposal would have had to justify a multi-billion-dollar price tag to a Congress that was already skeptical of NASA's ability to control costs. It would have had to demonstrate a compelling scientific rationale for visiting outer solar system targets that Voyager had already surveyed, at least in flyby mode. And it would have had to do all of this without the emotional and political leverage of a once-in-a-lifetime planetary alignment, creating a now-or-never urgency. Nobody made that proposal, not because they did not want to, but because the institutional conditions made it functionally impossible. The budget story contains another layer that most casual observers miss entirely. Even within NASA's declining budget, the allocation to planetary science fluctuated dramatically depending on internal priorities and external political pressures. During the 1970s, planetary science had briefly commanded nearly 50% of NASA's total space science budget. This was the period that produced Viking, Pioneer, and Voyager, but planetary science's share of the budget was not protected by any institutional guarantee. It rose and fell based on what other programs demanded. When the space station became a top priority in the late 1980s and 1990s, science budgets across NASA came under pressure. The station was enormously expensive to build and operate, requiring ongoing commitments that stretched across decades. Unlike a planetary mission with a defined end date, the station was an open-ended obligation. Every year it operated was another year its costs competed with everything else NASA wanted to do. The same pattern repeated with every major human spaceflight initiative. The Constellation program, which aimed to return humans to the Moon, consumed significant budget before being cancelled in 2010. The Space Launch System and Orion crew vehicle, which replaced Constellation, have absorbed over $23 billion in development costs since 2011. The Artemis program to land astronauts on the Moon continues to command billions annually. Each of these programs is justified on its own terms. Each serves real engineering and scientific objectives, but each also draws from the same finite pool of discretionary funding that would support a deep space exploration mission in the Voyager tradition. Human spaceflight has consistently received priority over robotic planetary science within NASA's budget. Not because robots are less scientifically productive per dollar, but because human missions carry greater political weight. Astronauts are visible, they generate media coverage, they inspire public enthusiasm, they create jobs in congressional districts where aerospace contractors build hardware. A robotic probe to the outer solar system, no matter how scientifically revolutionary, cannot match the political appeal of putting a human being on another world. This asymmetry has shaped NASA's budget priorities for decades, and it has consistently worked against the kind of long-duration, deep space robotic mission that a Voyager successor would represent. There is a subtler institutional factor at work as well, one that rarely gets discussed publicly but profoundly influences which missions get built. NASA does not operate in a vacuum. Its mission selections are guided by the decadal survey process, in which the National Academy of Sciences convenes panels of scientists to recommend priorities for each decade of research. These surveys are rigorous, thorough, and deeply influential. They represent the consensus of the scientific community about where the best science can be done with available resources. But the decadal survey process inherently favours missions with focused scientific objectives at specific destinations. A proposal to orbit Europa and study its subsurface ocean has a clear, well-defined scientific rationale. A proposal to orbit Saturn and study its ring dynamics has a clear rationale. A proposal to send a probe into the atmosphere of Uranus has a clear rationale. What does not fit neatly into this framework is a mission whose primary virtue is breadth. A single spacecraft that visits multiple planets in flyby mode, prioritizing coverage over depth. Voyager's scientific strategy, see everything once rather than study one thing deeply, was a product of the unique Grand Tour opportunity. It was the right approach for a one-time alignment that would not recur for nearly 2 centuries. But it is not the approach that the modern decadal survey process is designed to recommend, or that modern mission planners are structured to execute. The result is that every proposed mission to the outer solar system since Voyager has been designed as a dedicated mission to a single destination. Galileo went to Jupiter, Cassini-Huygens went to Saturn, Juno went to Jupiter. Each was a focused, deep investigation of one planetary system. Each produced extraordinary science, but none was designed to do what Voyager did, which was to survey the entire outer solar system in a single sweep. The institutional framework that selects and funds missions has evolved in a direction that makes Voyager-style exploration structurally unlikely, regardless of budget levels. Then there is the question of plutonium. Both Voyagers are powered by radioisotope thermoelectric generators fueled by plutonium-238. This isotope is not weapons-grade plutonium. It cannot be used in a nuclear bomb, but it is produced as a byproduct of nuclear weapons production. And when the United States scaled back its weapons programs after the Cold War, production of plutonium-238 essentially stopped. For decades, the United States had no domestic production capability for the isotope. NASA relied on dwindling stockpiles and small purchases from Russia. This created a bottleneck that constrained every deep space mission designed for destinations beyond Mars, where solar power is insufficient. The shortage of plutonium-238 directly affected mission planning throughout the 2000s and 2010s. NASA had to ration its remaining supply, allocating it only to the highest priority missions. The multi-mission radioisotope thermoelectric generator used on the Curiosity rover and later the Perseverance rover consumed significant portions of the available inventory. Any proposed outer planet mission had to demonstrate not just scientific merit, but also that enough plutonium existed to power it. The Department of Energy restarted limited production of plutonium-238 at Oak Ridge National Laboratory in 2015, with a target of roughly 1.5 kilograms per year. But production has been slow to ramp up, and the quantities remain modest compared to what a large outer planet mission would require. A Voyager-class spacecraft carried roughly 13 kilograms of plutonium dioxide across its 3 generators. Producing that quantity at current rates would take years, assuming no other mission was competing for the supply. The plutonium constraint is not insurmountable. Production is gradually increasing, but it adds another practical barrier to the kind of mission that Voyager represented, a barrier that did not exist in the 1970s, when Cold War weapons production ensured an ample supply of the isotope as a convenient byproduct. The plutonium story runs deeper than a simple supply shortage. It reveals how a decision made in one domain of government policy can quietly strangle an entirely unrelated scientific enterprise decades later. During the Cold War, the United States produced plutonium-238 as a byproduct of its nuclear weapons manufacturing infrastructure. The isotope was never the purpose of that infrastructure. It was a side effect, collected and stockpiled because it happened to be useful for applications that required long-duration, maintenance-free power sources in environments where no other option existed. Deep space probes, cardiac pacemakers, remote weather stations. The supply was abundant because the weapons complex was enormous. When the Cold War ended and the United States began scaling back its nuclear arsenal, the weapons production facilities that had generated plutonium-238 as a byproduct were decommissioned or converted. Production effectively ceased in the late 1980s. For more than 2 decades, the United States had no domestic capability to produce the isotope. NASA's stockpile, finite and irreplaceable, became a strategic resource that had to be rationed among competing missions. Every gram allocated to one spacecraft was a gram unavailable for another. Planning a new outer planet mission required not just scientific justification and political support, but a confirmed allocation of an isotope that the nation had stopped manufacturing. The Department of Energy's restart of production at Oak Ridge National Laboratory in 2015 was a critical step, but the output has been modest. The facility has gradually ramped toward a target of roughly 1.5 kilograms per year, a rate that has proven difficult to sustain consistently, and that falls well short of what ambitious future missions would demand. Even at that rate, accumulating the approximately 11 kilograms of plutonium dioxide that each Voyager carried in its 3 generators would require years of dedicated production, assuming no other mission was drawing from the same supply during that period. The Mars Perseverance rover, the Dragonfly mission to Titan scheduled for the late 2020s, and any future outer planet flagship would all compete for the same material. Plutonium-238 is not just a technical requirement. It is a bottleneck that constrains how many ambitious deep space missions the United States can fly in any given decade. The human cost of the lost decade is harder to quantify than budget figures, but arguably more damaging in the long run. An entire generation of planetary scientists spent the 1980s watching their career-defining mission concepts die in planning documents. Proposals for outer planet missions were written, reviewed, praised, and shelved. A Uranus orbiter was proposed and never funded. A Neptune mission was studied and never built. Concepts for follow-up probes to Jupiter's moons were drafted and archived. Each cancellation was not merely a bureaucratic outcome. It represented years of work by teams of scientists and engineers who had invested their professional lives in missions that would never fly. The psychological effect on the scientific community was corrosive. Young researchers who entered planetary science in the late 1970s, inspired by Voyager's discoveries, found themselves in a field with almost no funded flight missions. Career advancement in planetary science depends heavily on involvement with active missions. Data analysis, instrument development, and mission operations experience are the currency of professional advancement. Without new missions launching, that currency dried up. Some scientists left the field entirely, others shifted to adjacent disciplines. Those who remained spent years maintaining expertise on data from Voyager and Pioneer while waiting for the next opportunity to fly. When Galileo finally launched in 1989, it carried instruments whose designs had been frozen years earlier, using technology that was already aging by the time it left Earth. That 11-year drought was not just a pause in launches, it was an erosion of institutional knowledge, engineering momentum, and workforce continuity. Skills that are not exercised atrophy. Teams that are not building spacecraft lose their edge. Supplier relationships lapse. Testing facilities fall into disuse or are repurposed. Rebuilding all of this after a decade-long hiatus is slower and more expensive than maintaining it would have been. The lost decade demonstrated a principle that applies directly to the question of Voyager 3. Exploration programs do not pause gracefully. When you stop flying missions, you do not simply press a button and resume later at the same capability level. You lose people, expertise, infrastructure, and momentum. Restarting is harder than continuing ever would have been. The cost of the lost decade was not just the missions that were never flown. It was the erosion of the institutional capacity to fly them, a capacity that took years to rebuild and that remains more fragile than most people realize. Every one of these factors, the closed planetary alignment, the collapsed budget, the shuttle's dominance, the Challenger disaster, the station's ongoing costs, the human spaceflight priority, the decadal survey structure, the plutonium shortage, operated simultaneously. None of them alone would have been sufficient to prevent a Voyager successor. Together, they created an environment in which such a mission was almost impossible to propose, let alone approve and build. And this is the part of the story that most people never hear. The public narrative around Voyager is one of triumph. 2 small spacecraft conquered the outer solar system and sailed into interstellar space on technology less powerful than a digital watch. The story is told as an example of what humanity can achieve when it dares to explore, and that narrative is true. Voyager is one of humanity's greatest accomplishments, but the narrative is incomplete without the context. Voyager did not emerge from a system that routinely produces bold exploration. It emerged from a narrow historical window in which a unique planetary alignment, a briefly favourable budget environment, and a generation of engineers willing to over-design their hardware beyond what the bureaucracy authorised all converged at the same moment. When that window closed, it did not leave behind an institutional infrastructure capable of repeating the achievement. It left behind an agency that had traded deep space exploration for the space shuttle, that was struggling to maintain a human spaceflight program on a declining budget, and that had no astronomical forcing function comparable to the Grand Tour alignment to justify the next leap outward. The window was never just about the planets. It was about money, political will, institutional culture, propulsion technology, and a Cold War context that made large-scale government science spending politically viable. All of those conditions were temporary. All of them shifted within a decade of Voyager's launch, and none of them have returned in the same combination since. This is why asking, why have we not sent Voyager 3, is really asking a much bigger question. It is asking why the specific historical conditions that produced one of humanity's greatest explorations turned out to be so fragile, so contingent, and so difficult to reconstruct. The planets moved on, the budgets shrank, the priorities shifted, the plutonium ran low, the institutional culture evolved toward risk aversion and focused investigations rather than sweeping surveys. And somewhere in the gap between what Voyager achieved and what came afterward, something essential was lost, not the desire to explore. Scientists have never stopped proposing ambitious outer solar system missions, not the technical capability. Modern spacecraft are vastly more capable than the Voyagers in every measurable way. What was lost was the alignment, not of planets, but of all the human factors that have to converge before a civilization commits to sending a machine to the edge of the solar system and beyond. But knowing that the window closed does not fully explain the absence of Voyager 3, because NASA did build other missions to the outer planets after Voyager. It sent Galileo to Jupiter, it sent Cassini to Saturn, it sent New Horizons to Pluto. Each of these missions was extraordinary in its own right. Each pushed the boundaries of what robotic exploration could accomplish, and yet none of them was Voyager. None of them attempted what Voyager attempted. None of them was built in the same spirit or designed with the same ambition. What made those missions different, and why the difference matters, is the story that comes next. After the lost decade ended, NASA did return to the outer solar system. It sent sophisticated machines to Jupiter and Saturn. It dispatched a small, fast probe to Pluto. It built orbiters that circled gas giants for years, dropping instruments into alien atmospheres and photographing moons in resolution that would have seemed miraculous to the scientists who first squinted at Voyager's grainy television images. These were not failures. They were triumphs. And yet, taken together, they reveal something important about how the philosophy of deep space exploration changed after Voyager, and why that change made a true successor impossible. Galileo was the first major outer planet mission after Voyager, and its tortured history illustrates nearly everything that went wrong with the institutional conditions for ambitious exploration. The spacecraft was approved in 1977, the same year the Voyagers launched. It was designed as a Jupiter orbiter and atmospheric probe, intended to spend 2 years circling the giant planet and studying its moons, magnetosphere, and atmosphere in far greater detail than Voyager's brief flybys had allowed. The concept was magnificent. Where Voyager had raced past Jupiter in a matter of days, capturing snapshots of a world in motion, Galileo would settle into orbit and watch. It would observe Io's volcanoes erupting over months. It would map Europa's fractured ice in high resolution. It would deploy a probe directly into Jupiter's atmosphere to measure composition, temperature, and pressure as it descended through the cloud layers. Galileo was deeper science, closer study, longer engagement, but Galileo was not Voyager. It was not designed to survey the outer solar system. It was designed to study one planet, and the journey to get it there became a cautionary tale about what happens when institutional priorities collide with scientific ambition. Construction began in 1978. The spacecraft was supposed to launch in 1982 aboard the Space Shuttle using a Centaur upper stage that would send it directly to Jupiter. That launch date slipped to 1984, then 1985. Each delay added cost. Each cost increase generated political scrutiny. Then Challenger exploded in January 1986, grounding the shuttle fleet and eliminating the Centaur upper stage option entirely. NASA could no longer fly a liquid-fueled rocket inside the shuttle's cargo bay alongside a human crew. The risk was deemed unacceptable. Engineers redesigned Galileo's trajectory to use a less powerful solid-fuel inertial upper stage. Without the Centaur's power, the spacecraft could not reach Jupiter directly. Instead, it would need to fly past Venus once and Earth twice, using gravity assists to gradually build up enough velocity to reach the outer solar system. The new trajectory added 4 years to the flight time. Galileo finally launched in October 1989, 7 years late, aboard the shuttle Atlantis. It would not arrive at Jupiter until December 1995, 17 years after construction began. During the long coast to Jupiter, disaster struck again. Galileo's high-gain antenna, a large umbrella-shaped dish essential for transmitting data at high rates back to Earth, failed to deploy fully. Several of its ribs remained stuck despite years of troubleshooting attempts. The antenna was supposed to transmit data at 134,000 bits per second. Without it, the spacecraft was limited to its low-gain antenna, which transmitted at only tens of bits per second, a reduction by a factor of thousands. Engineers developed clever data compression algorithms that partially compensated for the loss, but Galileo could never return the volume of data it was designed to produce. Images that should have been transmitted in minutes took hours. The full scientific return was permanently diminished by a mechanical failure that might have been caught and fixed if the spacecraft had not spent over a decade sitting in storage and transit, Despite these setbacks, Galileo produced extraordinary science. It confirmed the existence of a subsurface ocean on Europa, strengthening the case that this frozen moon might harbour conditions suitable for life. It observed Io's volcanoes in exquisite detail, watching eruptions evolve over time. It measured Jupiter's atmosphere directly through its descent probe, which survived for 57 minutes before being crushed by pressure. It discovered that Ganymede possesses its own internally generated magnetic field, the only moon in the solar system known to have one. The mission was extended twice beyond its original 2-year plan, ultimately operating in Jupiter orbit for nearly 8 years before being deliberately crashed into Jupiter's atmosphere in September 2003 to prevent any possibility of contaminating Europa with Earth microbes. Galileo proved that orbital missions to the outer planets could produce science far deeper than any flyby. But it also proved something else. It took 17 years from construction start to Jupiter arrival. It cost roughly $1.6 billion. Its most important communication system broke. Its launch was delayed nearly a decade by the shuttle program's failures, and it visited one planet. Voyager had visited 4 planets, dozens of moons, and multiple ring systems across 2 spacecraft for roughly half the inflation-adjusted cost, and both Voyagers were still operating decades later. This comparison is not a criticism of Galileo. Orbital science and flyby science serve different purposes. You cannot study a subsurface ocean from a spacecraft that spends 3 days in the neighborhood and then vanishes toward the next planet. Galileo's deep, sustained investigation of the Jovian system was scientifically essential and could not have been done any other way. But the comparison reveals a fundamental shift in how NASA approached the outer solar system after Voyager. The agency moved from breadth to depth, from surveying the landscape to excavating individual sites. And while that shift produced superb science at specific destinations, it also meant that no single mission would ever again attempt what Voyager attempted, which was to show humanity the entire outer solar system in one grand sweep. Cassini-Huygens continued this pattern and expanded it. Cassini was a joint mission between NASA and the European Space Agency, designed to orbit Saturn and study the ringed planet, its moons, and its magnetosphere for at least 4 years. The Huygens probe, built by ESA, would detach from Cassini and descend through the atmosphere of Titan, the moon whose thick nitrogen haze had tantalized scientists ever since Voyager 1's flyby in 1980. Cassini launched in October 1997 and reached Saturn in July 2004, after a 7-year journey that included gravity assists from Venus twice, Earth once, and Jupiter once. The mission was a masterpiece. Cassini orbited Saturn for 13 years, far exceeding its original 4-year plan. It completed 294 orbits of the planet. It executed 127 close flybys of Titan and 23 close flybys of Enceladus. It discovered that Enceladus, a tiny ice moon roughly 300 miles across, was venting plumes of water vapor and ice particles from fractures near its south pole, suggesting the existence of a subsurface ocean in contact with a rocky core, conditions that make Enceladus one of the most compelling candidates for extraterrestrial life in the solar system. It mapped Titan's surface through the hydrocarbon haze using radar, revealing lakes and seas of liquid methane and ethane near the poles, river channels carved by hydrocarbon rain, and vast dune fields of organic particles near the equator. Huygens descended through Titan's atmosphere on January 14, 2005, returning data for roughly 72 minutes after landing, the most distant surface landing ever achieved by a human-made spacecraft. Cassini's total mission cost was approximately $3.9 billion, making it one of the most expensive robotic missions NASA has ever flown. That cost reflected the spacecraft's enormous complexity, its 13-year operational lifetime, its extensive instrument suite, and the deep involvement of the European Space Agency. By every scientific measure, Cassini was worth every dollar. It transformed our understanding of the Saturnian system from a collection of telescopic observations and Voyager flyby snapshots into a richly detailed, dynamically evolving planetary environment. But Cassini was not Voyager either. It spent 13 years at one planet. It did not visit Uranus. It did not visit Neptune. It did not attempt a grand survey of multiple worlds. It was a deep dive, not a broad stroke, and its $3.9 billion price tag illustrated a paradox that would haunt every subsequent proposal for outer planet exploration. Modern flagship missions to the outer solar system are extraordinarily expensive. They are expensive because they are complex. They are complex because the scientific community demands high-resolution instruments, long operational lifetimes, extensive data return capabilities, and the kind of redundancy and fault protection that ensures a multi-billion-dollar investment does not fail in the void between planets. The same institutional pressures that make modern missions more capable than Voyager also make them more costly, more time-consuming to develop, and more politically difficult to justify. Voyager succeeded in part because it was cheap by modern standards. The entire Voyager program through the Neptune encounter cost $865 million, roughly $3.5 billion in today's currency, for 2 spacecraft visiting 4 planets across 12 years. Cassini cost about the same amount for 1 spacecraft at 1 destination. The cost per planet visited tells the story. Voyager spent less than $1 billion inflation-adjusted dollars per planet explored. Cassini spent nearly $4 billion on a single planetary system. Both approaches produced brilliant science, but only one of them was affordable enough to justify as a survey mission. And the conditions that made Voyager affordable, simpler instruments, lower data rates, less institutional overhead, fewer safety requirements, and a planetary alignment that eliminated the need for expensive propulsion maneuvers no longer exist. New Horizons represents a different approach entirely, and in some ways it is the closest thing to a Voyager successor that NASA has produced. But even New Horizons illustrates why the Voyager model has proven so difficult to replicate. New Horizons launched on January 19, 2006, aboard an Atlas V rocket with a powerful upper stage that made it the fastest spacecraft ever launched from Earth at the time. Its target was Pluto, a world that Voyager 1 could theoretically have visited instead of Titan if NASA had chosen a different trajectory at Saturn. The decision to prioritize Titan over Pluto in 1980 meant that Pluto remained unexplored for another 35 years. New Horizons reached Pluto on July 14, 2015, after a 9.5-year journey. The encounter was a fast flyby, not an orbital insertion. The spacecraft screamed past Pluto at over 30,000 miles per hour, collecting data furiously during a window of intense observation lasting roughly 24 hours. What it found was astonishing. Pluto was not a dead, frozen ball of ice. Its surface showed vast plains of nitrogen ice, towering mountains of water ice, evidence of past and possibly ongoing geological activity, a thin nitrogen atmosphere with multiple haze layers, and a heart-shaped feature that became one of the most iconic images in planetary science. The largest moon, Charon, displayed its own geological complexity, including a massive canyon system and evidence of past cryovolcanism. New Horizons was built under NASA's New Frontiers program, a medium-cost mission class with a budget cap of roughly $700 million at the time of selection. This made it far cheaper than a flagship mission like Cassini, but also far less capable. The spacecraft weighed roughly 1,054 pounds, about 60% of each Voyager's mass. It carried 7 scientific instruments compared to Voyager's 10. Its power source was a single radioisotope thermoelectric generator, producing roughly 245 watts at launch, about half of what each Voyager carried. Its data transmission rate from Pluto was roughly 1,000 bits per second, meaning it took over 15 months to transmit all of the data collected during its brief flyby back to Earth. New Horizons was a triumph of efficiency. It accomplished its primary mission at a fraction of a flagship's cost and delivered science that justified every dollar. After Pluto, it continued outward and performed a flyby of Arrokoth, a small Kuiper Belt object, on January 1st, 2019, revealing a contact binary shaped like a snowman, one of the most primitive and undisturbed objects ever observed up close. But New Horizons was explicitly not a Voyager. It visited one major target in flyby mode. It did not visit any of the 4 giant planets. It carried fewer instruments, returned data more slowly, and had no possibility of the kind of multi-planet survey that defined Voyager's mission. It was built to be cheap, fast, and focused, the opposite of the expansive, system-spanning philosophy that made Voyager iconic. The New Frontiers cost cap that enabled New Horizons to exist also constrained what it could attempt. You cannot build a Voyager under a $700 million ceiling. The ambition does not fit inside the budget. This brings us to the structural reason why no Voyager 3 has emerged from NASA's modern mission architecture. Beginning in the 1990s, NASA reorganized its planetary exploration program into a tiered system of mission classes. Discovery missions are the smallest and cheapest, with cost caps currently under $500 million. They are designed for focused investigations at single targets. Think the Mars Pathfinder rover or the Messenger Mercury orbiter. New Frontiers missions occupy the middle tier, with cost caps around $900 million. They allow somewhat more ambitious objectives, but still require tight scientific focus. Think New Horizons at Pluto or Juno at Jupiter. Flagship missions sit at the top, with budgets typically exceeding $2 billion. These are the most capable and most expensive. Think Cassini at Saturn, or the Europa Clipper currently en route to study Jupiter's ocean moon. This tiered system was a deliberate response to the cost overruns and schedule delays that plagued missions like Galileo. By imposing cost caps and competitive selection processes, NASA created a pipeline that produces a steady cadence of missions, rather than placing all its bets on a single enormous project that might fail or be cancelled. The system works. Since its implementation, NASA has launched more planetary missions per decade than it did during the lost decade of the 1980s. The quality of science has been consistently high. The failure rate has been low, but the tiered system has an unintended consequence. It makes Voyager-class missions almost impossible to propose. A mission that visits multiple outer planets in flyby mode does not fit neatly into any tier. It is too expensive for New Frontiers. It is too broad for a flagship, which is expected to focus intensively on a single target to justify its cost. It does not align with the decadal survey process, which recommends specific scientific priorities at specific destinations rather than endorsing sweeping surveys. A scientist who proposed a modern Voyager, a spacecraft designed to fly past Uranus, Neptune, and then continue into interstellar space, would face immediate resistance on multiple fronts. The planetary science community would ask why a flyby is preferable to an orbiter that could study one of those planets in depth. The budget reviewers would question whether a multi-destination mission offers better scientific return per dollar than multiple focused missions to individual targets. The decadal survey panel would struggle to rank it against competing proposals that address more specific scientific questions. The irony is painful. Voyager succeeded precisely because it was broad. Its flybys of 4 planetary systems produced discoveries that no one anticipated, discoveries that could not have been predicted in advance, and therefore could not have been used to justify a focused mission. Active volcanoes on Io, subsurface oceans on Europa, hydrocarbon rain on Titan, nitrogen geysers on Triton. None of these were expected. None of them appeared in any pre-mission scientific justification. They were found because Voyager went to places no spacecraft had visited before and looked at everything it could. The breadth was the feature, not the bug. And the modern mission architecture has no mechanism for reproducing it. The most revealing case study in the gap between scientific ambition and institutional reality involves the 2 planets that Voyager 2 visited and that no spacecraft has returned to since. Uranus and Neptune, the ice giants of the outer solar system, remain the least explored major planets. Voyager 2's flybys in 1986 and 1989 provided humanity's only close-up observations of these worlds. Everything we know about their atmospheres, their magnetic fields, their ring systems, and their moons comes from a few days of data collected by a spacecraft flying past at tens of thousands of miles per hour with instruments designed in the early 1970s. That is the entirety of the observational record. 2 brief encounters, nearly 4 decades ago, using technology that predates the personal computer. In 2022, the National Academies of Sciences released its Planetary Science and Astrobiology Decadal Survey for 2023 through 2032, the most influential document in determining which missions NASA will prioritize over the coming decade. The survey's top priority recommendation for a new flagship mission was a Uranus orbiter and probe. Not Mars, not Europa, not Enceladus, Uranus. The panel of scientists who evaluated dozens of competing proposals concluded that returning to an ice giant represented the single most important thing NASA's planetary science program could do next. The reasoning was compelling on multiple levels. Uranus is genuinely strange. Its rotational axis is tilted 98 degrees from the vertical, an orientation so extreme that its poles take turns pointing almost directly at the Sun over the course of its 84-year orbit. The magnetic field anomaly that baffled scientists during Voyager 2's flyby remains unexplained decades later, with no dynamo model able to account for the extreme tilt and offset that make Uranus unique among the planets. Its atmosphere appeared almost featureless during Voyager 2's flyby, but subsequent observations from Earth-based and space-based telescopes have revealed seasonal changes, cloud activity, and atmospheric dynamics that the brief flyby could not have detected. Its 28 known moons include Miranda, a small world whose surface displays some of the most dramatic geological features in the solar system, including a cliff face nearly 12 miles high. 5 of the larger moons show evidence of past or possibly present geological activity that could involve subsurface oceans. The ring system, while less dramatic than Saturn's, contains dark, narrow rings whose composition and dynamics remain poorly understood. But the most powerful argument for studying Uranus and Neptune has nothing to do with the specific peculiarities of those two planets. It has to do with what they represent in the broader context of the galaxy. Over the past 2 decades, exoplanet surveys have revealed that the most common type of planet in the Milky Way is not a rocky world like Earth. It is not a gas giant like Jupiter or Saturn. It is something in between. Planets roughly 2 to 4 times the diameter of Earth, with masses ranging from a few times to 20 times that of our own world, appear to be the dominant planetary type in the galaxy. These worlds, often called sub-Neptunes or mini-Neptunes, have no analogue in our inner solar system. The closest analogues we have are Uranus and Neptune themselves. This means that understanding ice giants is not just a matter of completing our survey of the local solar system. It is a prerequisite for understanding the most common type of planet in the universe. Every time an astronomer detects a sub-Neptune orbiting a distant star and tries to interpret its atmosphere, its interior structure, or its potential habitability, they are working with models built on data from 2 brief Voyager flybys and decades of distant telescopic observation. The models are incomplete, the data is thin, the uncertainties are large. A dedicated orbiter mission to Uranus, equipped with modern instruments and designed to spend years studying the planet and its moons, would provide the ground truth needed to understand not just one world, but an entire category of worlds that dominates the planetary census of the galaxy. The Decadal Survey recognized this. Its recommendation was clear, well-reasoned, and unanimous among the panel members. And yet, as of 2026, the Uranus orbiter and probe has not been formally approved for development. NASA has funded preliminary studies and technology development. Engineers are working on mission concepts, but the transition from recommended priority to funded program requires a sustained budget commitment of several $1 billion over more than a decade, and that commitment has not materialized. The mission faces the same structural challenges that have delayed or killed outer planet proposals for decades. It is expensive. It requires a long development timeline. It needs plutonium-238 for its power source. It must compete for funding against ongoing commitments to Mars sample return, the Europa Clipper, the Artemis human spaceflight program, and the operational costs of existing missions. The Decadal Survey can recommend. Only Congress can fund. The Uranus orbiter would not be a Voyager. It would be a focused investigation of a single planetary system, closer in philosophy to Cassini or Galileo than to the Grand Tour. but its struggles to move from recommendation to reality illuminate the same pattern that has prevented a true Voyager successor. Even when the scientific case is overwhelming, even when the expert community reaches consensus on what should be done next, the institutional and political machinery required to convert that consensus into a launched spacecraft operates on timescales and under constraints that have little to do with scientific merit. The best mission concept in the world is just a document until someone writes the check. Meanwhile, the concept of a dedicated interstellar probe, a spacecraft designed specifically to travel beyond the heliosphere and study interstellar space, has been studied repeatedly but never funded. The most developed proposal is the interstellar probe concept led by the Johns Hopkins University Applied Physics Laboratory. This mission would launch on a heavy-lift rocket in the late 2030s or early 2040s, perform a Jupiter gravity assist to achieve a speed of roughly 6 to 7 astronomical units per year, and reach distances of 300 to 1,000 astronomical units within 50 years. For reference, Voyager 1 is currently travelling at about 3.6 astronomical units per year and is approximately 170 astronomical units from the Sun. The interstellar probe would be nearly twice as fast and would carry modern instruments vastly more capable than Voyager's aging detectors. The science case is compelling. Voyager 1 and 2 crossed the heliopause with instruments that were already decades old, and many of which had been shut down to conserve power. Their measurements of the interstellar medium, while groundbreaking, were incomplete. Key questions remain unanswered. What is the global structure of the heliosphere? How does the Sun's magnetic bubble interact with the surrounding interstellar gas and dust? What is the nature of the interstellar medium in the region immediately beyond the Sun's influence? These are questions that a dedicated probe with modern instrumentation could address definitively. But as of 2026, the interstellar probe remains in the conceptual phase. It achieved a maturity level of 4 during its study period. Concept studies and white papers were submitted to support NASA's 2024 to 2033 Heliophysics Decadal Survey. The survey acknowledged the scientific importance of the concept, but acknowledging importance and committing billions of dollars in funding are very different things. No launch has been authorized. No development contract has been awarded. The baseline launch window of 2036 to 2041 remains a planning target, not a programmatic commitment. The mission could still happen. It could also join the long list of proposed interstellar and outer planet missions that were studied, praised, and never built. NASA's IMAP mission, the Interstellar Mapping and Acceleration Probe, launched in September 2025 and is now operational at the Sun-Earth Lone Lagrange point, roughly 1 million miles from Earth. IMAP carries 10 scientific instruments designed to study the heliosphere's boundaries and the interaction between the solar wind and the interstellar medium. It is producing valuable science, but IMAP does not travel beyond the inner solar system. It observes the heliosphere remotely, detecting energetic neutral atoms and other signatures that reveal conditions at the boundary without actually going there. It is a complement to Voyager, not a successor. It fills in the map from a safe distance. It does not extend the journey. China has proposed its own interstellar exploration effort, called Interstellar Express or Shenzhou, which envisions sending 2 probes in opposite directions through the heliosphere. The concept originated in 2014 and has undergone feasibility studies. One probe would travel through the nose of the heliosphere, the direction the Sun is moving through the galaxy, while the other would head toward the tail. The program has discussed possible launch dates around 2024 or 2025 for initial missions, though as of 2026, no confirmed launch has occurred for the interstellar components. If China proceeds, it would represent the first dedicated interstellar probe mission by any nation, a milestone that NASA has discussed for decades but never funded. The Breakthrough Starshot Initiative, funded by private philanthropist Yuri Milner, represents the most radical approach to interstellar travel yet proposed. The concept envisions launching thousands of gram-scale spacecraft, each equipped with a light sail, and accelerating them to approximately 20% of the speed of light using a ground-based laser array. At that speed, A probe could reach the Alpha Centauri star system in roughly 20 years. The concept is theoretically fascinating but faces enormous engineering challenges that remain far from solved, including building a sufficiently powerful laser array, designing functional spacecraft that weigh only a few grams, and communicating with probes across distances of 4 light-years using hardware smaller than a postage stamp. Breakthrough Starshot is a research program, not a funded mission, and its timeline for any actual launch remains highly uncertain. The landscape of post-Voyager exploration, taken as a whole, reveals a consistent pattern. Scientists and engineers have never stopped wanting to go further. The ideas are abundant, the proposals are detailed, the technology is plausible and in many cases already demonstrated. What is missing is not imagination. What is missing is the convergence of political will, budget priority, institutional alignment, and astronomical opportunity that briefly existed in the 1970s and made Voyager possible. Every mission that came after Voyager was shaped by a different set of constraints. Galileo was shaped by the shuttle's failures. Cassini was shaped by the need for international cost-sharing. New Horizons was shaped by a cost cap that limited its scope. The Interstellar probe is shaped by the absence of a confirmed budget line. Each of these missions was excellent on its own terms. Each advanced human knowledge of the outer solar system in ways that Voyager's flybys could not. But none of them was built in the same spirit as Voyager. None was designed to survey the unknown. None embraced the same tolerance for ambiguity, the same willingness to go somewhere simply because no one had been there before, the same institutional audacity of building a 4-year spacecraft and quietly designing it to last 50. That spirit did not die because people stopped believing in it. It faded because the structures that govern how space missions are proposed, evaluated, funded, and built evolved in directions that reward focus over breadth, predictability over risk, and incremental depth over sweeping ambition. The modern system produces better science per mission than Voyager delivered at any single destination, but it cannot produce a Voyager. The architecture does not allow it. The budget structure does not support it. The evaluation criteria do not favour it. And the astronomical circumstances that made the original Grand Tour possible will not return for another century and a half. The missions that came instead of Voyager 3 were not lesser missions. They were different missions, built by a different system for a different era under different constraints. Understanding why they were different is essential to understanding why the absence of a true Voyager successor reflects something larger than a single cancelled program or a single insufficient budget. It reflects a transformation in how an entire civilization approaches the question of how far it is willing to reach into the unknown and what price it is willing to pay for the answer. What that transformation means, and what the fading signal from Voyager 1 tells us about the kind of future we chose not to build, is where this journey arrives at its final destination. On April 17th, 2026, an engineer at NASA's Jet Propulsion Laboratory in Pasadena, California, sent a sequence of commands to a spacecraft more than 15 billion miles away. The signal travelled at the speed of light. It took 23 hours to arrive. When it reached its destination, the commands instructed Voyager 1 to shut down its low-energy charged particles instrument, a device that had been operating almost continuously since 1977. The instrument had measured ions, electrons, and cosmic rays originating from our solar system and our galaxy. It had helped determine the precise moment when Voyager 1 crossed the heliopause and entered interstellar space. It had provided data from a region of the universe that no other instrument in human history had ever sampled directly. And now it was turned off, not because it was broken, because there was not enough electricity to keep it running. Voyager 1 now operates with 2 functioning science instruments out of the 10 it carried at launch. One listens to plasma waves in the interstellar medium. The other measures magnetic fields. Together, they draw a tiny fraction of the power that the spacecraft's 3 radioisotope thermoelectric generators can still provide. Those generators, fueled by the slow radioactive decay of plutonium-238, produced 470 watts when Voyager launched. They now produce less than half that amount. Every year, approximately 4 more watts disappear. The spacecraft is dying the way a candle dies, not all at once, but in a slow, steady dimming that has been underway for nearly 5 decades. The engineering team has known this was coming. Years ago, the Voyager science and operations teams sat down together and agreed on the order in which instruments and heaters would be switched off as power declined. They created a roadmap for a long, managed decline, each step buying a few more months or a year of continued operations. The low-energy charged particles experiment on Voyager 2 had already been shut down in March 2025. Now Voyager 1 followed. Of the 10 identical instrument sets on each spacecraft, 7 have been turned off so far. The remaining instruments measure what they can with what power they have, whispering their findings back to Earth on a transmitter that radiates roughly 12 watts, about the output of a dim refrigerator light bulb, across a distance that light itself needs nearly a full day to cross. Later in 2026, around mid-November, Voyager 1 is expected to reach a milestone that has no scientific significance, but carries enormous emotional weight. It will become the first human-made object to travel 1 full light day from Earth. At that distance, a radio signal sent from Pasadena in the morning will not reach the spacecraft until the following morning. A reply will not arrive until the morning after that. A simple 2-way exchange will span 2 full Earth days. The distance is roughly 25.9 billion kilometers. No human artifact has ever been so far from home. The team that keeps both Voyagers functioning is remarkably small. At its peak, during the planetary encounters of the 1980s, the Voyager operations staff numbered in the hundreds. Today, the full-time team consists of roughly a dozen people working out of a cluster of offices at the Jet Propulsion Laboratory. Some of them have spent their entire careers on this single mission. Others joined decades after launch, inheriting a spacecraft they had to learn like an ancient language. The flight software runs on assembly code written in the 1970s. The command sequences must be composed for computers with less memory than a modern musical greeting card. Debugging a problem on Voyager means thinking like an engineer from a different technological era, reasoning through hardware constraints that no university teaches anymore, and no other active mission shares. When a senior Voyager engineer retires, what walks out the door is not just expertise, it is fluency in a dead dialect of spacecraft operations that exists nowhere else on Earth. There is no textbook for commanding a machine that has been flying for nearly 50 years on hardware that predates the personal computer. The knowledge lives in the people, and the people are finite. This is its own quiet form of the same problem that prevented Voyager 3. The institutional knowledge required to sustain extraordinary exploration does not maintain itself. It must be deliberately preserved, funded, and transferred. The Voyager operations team has managed this transfer successfully for decades, training new engineers on systems older than they are, maintaining continuity across a span of time that would challenge any human institution. But their work is invisible to the public. No one outside the space community celebrates the people who keep a dying spacecraft alive. The mission endures because a handful of people refuse to let it end. The engineers are not sentimental people by training, but they understand what Voyager represents. They are currently developing an ambitious power conservation maneuver they have nicknamed the Big Bang, a coordinated swap of multiple powered systems on each spacecraft, replacing older components with lower power alternatives in a single, carefully sequenced operation. The plan is to test the procedure on Voyager 2 first, in May and June of 2026. Because Voyager 2 has slightly more power available and is closer to Earth, making it a safer test subject. If the test succeeds, the team will attempt the same procedure on Voyager 1 no sooner than July. If it works, there is even a slim possibility that the low-energy charged particles instrument could be switched back on. The engineers hope to keep at least one instrument operating on each spacecraft into the early 2030s. After that, the power will be too low to sustain any science. The transmitters will eventually fall silent. The spacecraft will continue traveling outward at roughly 38,000 miles per hour, carried by its own momentum through the interstellar void. They will orbit the center of the Milky Way alongside the stars, drifting for millions, then billions, then trillions of years. Long after the sun has exhausted its hydrogen fuel and swollen into a red giant that swallows the inner planets, long after the Earth has been vaporized or flung into the darkness, the Voyagers will still be out there, silent, intact, carrying their golden records engraved with images and sounds from a civilization that may no longer exist. This is the image that should haunt anyone who asks why humanity never sent Voyager 3. Not the budget charts, not the decadal survey recommendations, not the tiered mission architecture, or the plutonium supply chain. Those are the mechanisms. The image of a dying spacecraft still crawling outward through interstellar space on the momentum of a 1977 launch is the meaning. Because Voyager 1 is not just a spacecraft running out of power, it is a physical embodiment of a moment in human history when a civilization chose to reach as far as it could into the unknown, succeeded beyond all reasonable expectation, and then quietly decided not to do it again. That decision was never made explicitly. No president stood at a podium and announced that humanity would stop exploring the deep solar system. No congressional committee voted to cancel the future of interstellar science. No scientific panel declared that the outer planets were no longer interesting. The decision emerged gradually, invisibly, as the accumulated result of thousands of smaller decisions made by hundreds of institutions over decades. Each individual decision was defensible. Each budget allocation reflected real competing priorities. Each mission selection followed a rational process designed to maximize scientific return per dollar spent. No single person or institution is to blame, and yet the outcome is undeniable. The boldest model of deep space exploration that humanity ever demonstrated was never repeated. This is not a story about villains. It is a story about how extraordinary achievements can be orphaned by the very institutions that produced them. The Voyager program emerged from a set of conditions that were, in retrospect, genuinely anomalous. A once-in-175-year planetary alignment created an astronomical deadline that overrode bureaucratic caution. A post-Apollo budget environment that briefly channeled significant funding toward planetary science provided the financial foundation. A Cold War context that made large government science investments politically viable ensured congressional support. A generation of engineers trained in the Apollo tradition brought a cultural willingness to over-design hardware, accept managed risk, and pursue objectives that exceeded their official mandate. A scientific community still young enough and ambitious enough to dream of surveying the entire outer solar system in a single campaign supplied the intellectual energy. Every one of those conditions was temporary. The alignment passed, the budgets contracted, the Cold War ended, the Apollo-trained engineers retired, the scientific community adapted to the reality of constrained resources and focused its ambitions accordingly. What replaced those conditions was not worse in every respect. The modern system of tiered missions, cost caps, and decadal survey priorities produces excellent science with impressive efficiency. But it is a system optimized for depth rather than breadth, for predictability rather than audacity, for answering specific questions rather than discovering what questions to ask. There is a way of thinking about civilizational progress that assumes exploration is cumulative. Each achievement builds on the last. Each generation pushes further than the one before. The story moves in one direction. Outward, upward, forward. This assumption is so deeply embedded in how we talk about space exploration that it feels almost sacrilegious to question it. We reach the moon, so naturally we will reach Mars. We sent probes to the outer planets, so naturally we will send probes to the stars. The arc of exploration bends toward expansion. Voyager's legacy challenges this assumption in a way that most people find deeply uncomfortable, because the record shows that exploration is not cumulative. It is episodic. It happens in bursts, driven by specific historical circumstances that align for brief periods and then disperse. The age of exploration that sent European ships across the Atlantic in the 15th and 16th centuries was driven by a particular combination of navigational technology, economic incentive, political competition, and cultural appetite for risk. When those conditions changed, the great voyages slowed and eventually stopped. Centuries passed before anything comparable occurred. The Apollo program was driven by Cold War competition, presidential mandate, and an unprecedented allocation of national resources. When those conditions changed, human beings stopped traveling beyond low Earth orbit. More than half a century later, they still have not returned to the Moon, though the Artemis program aims to change that. The Voyager program fits the same pattern. It was driven by unique planetary alignment, a brief window of favourable funding, and an institutional culture that tolerated risk and rewarded ambition. When those conditions changed, the kind of mission Voyager represented stopped being built. Not because anyone decided to stop exploring, but because the specific combination of factors that enabled that particular kind of exploration no longer existed, and no one knew how to reassemble them. This is the deeper meaning of the question in this video's title. Asking why we have not sent Voyager 3 is not really asking about one missing mission. It is asking whether humanity's relationship with deep space exploration is fundamentally episodic, whether our most ambitious journeys are isolated spikes of activity separated by long periods of consolidation or retreat, and whether the conditions required to produce another spike are within our control or largely dependent on historical accident. The honest answer is uncomfortable. The conditions that produced Voyager were largely accidental. No one planned for the planets to align in the 1970s. No one designed the post-Apollo budget environment to favour planetary science. No one orchestrated the cultural moment that allowed JPL engineers to build spacecraft, rated for 5 years, and quietly design them to survive 50. These things converged because of historical contingency, not because of deliberate civilizational strategy. And when they stopped converging, the exploration they enabled stopped too. This does not mean that a Voyager successor is impossible. It means that waiting for the right conditions to emerge on their own is a strategy that has already failed for 5 decades. If humanity wants to send another spacecraft into the deep outer solar system and beyond, it will have to create the conditions deliberately rather than hoping they occur naturally. That means sustained political commitment to funding deep space exploration as a priority rather than a budget residual. It means developing next-generation propulsion technologies, such as nuclear electric or advanced solar sail systems, that can compensate for the absence of a Grand Tour alignment. It means investing in plutonium-238 production at rates sufficient to power ambitious missions without rationing. It means building an institutional framework that can support 50-year mission lifetimes across multiple generations of engineers, scientists, and political administrations. And it means accepting that some of the most important discoveries in deep space exploration cannot be predicted in advance, which means that the scientific case for going cannot be reduced to a list of specific questions to be answered at specific destinations. All of this is possible. None of it is easy. And none of it is currently happening at the scale required. The Interstellar probe concept studied by Johns Hopkins Applied Physics Laboratory represents perhaps the closest thing to a real Voyager successor on the horizon. If funded and built, it would be the first spacecraft specifically designed to explore interstellar space with modern instruments. It would travel faster than Voyager. It would carry detectors capable of measurements that Voyager's aging hardware can no longer perform. It would address fundamental questions about the heliosphere's global structure and the nature of the local interstellar medium, and it would do something that no mission since Voyager has attempted. It would leave. Not orbit a planet, not circle a moon, not park at a Lagrange point. It would head outward, past the boundary of the sun's influence, into the space between the stars, and keep going for 50 years. But the Interstellar probe is not approved. It is not funded. It is a concept study with white papers and a favourable mention in a decadal survey. Converting it from a concept into a launch spacecraft will require exactly the kind of sustained political commitment and institutional alignment that has been absent since the Voyager era. The mission's baseline launch window of 2036 to 2041 is a planning horizon, not a promise. History is littered with proposed missions that were studied, praised, and never built. The Interstellar probe could join that list, or it could become the mission that finally extends the journey Voyager began. The outcome depends entirely on choices that have not yet been made, by institutions and governments that have not yet committed. There is a particular kind of loss that occurs when a civilization demonstrates what it is capable of and then fails to follow through. It is not the same as never having tried. It is worse, because the achievement itself creates an expectation. It establishes a standard. It shows the world and the civilization itself what is possible. And when the follow-through never comes, the gap between what was demonstrated and what was sustained becomes a permanent feature of the historical record, a scar on the timeline, a reminder that capability and commitment are not the same thing. Voyager demonstrated that humanity could build machines capable of crossing the solar system and entering interstellar space. It demonstrated that those machines could function for decades beyond their design lifetimes. It demonstrated that the outer solar system was not a barren wasteland, but a collection of dynamic, complex worlds teeming with phenomena that no one had predicted. It demonstrated that deep space exploration could produce scientific returns vastly disproportionate to its cost. And then, having demonstrated all of this, the civilization that built it moved on to other things. Not bad things, not unworthy things. Space stations, Mars rovers, Hubble, James Webb. Missions that expanded human knowledge in other directions. But the particular direction that Voyager pointed, outward, past the planets, into the space between the stars, was left unattended. The two Voyagers are still out there. As of this moment, Voyager 1 is the most distant human-made object in existence, farther from Earth than any artifact our species has ever produced. Voyager 2, following a different trajectory, is the second most distant. They are travelling in roughly opposite directions through interstellar space, separating from each other and from Earth at a combined rate of nearly 70,000 miles per hour. Every second, the distance between them and everything humanity has ever known grows by about 20 miles. They carry no fuel for course corrections. Their thrusters have been dormant for years. Their cameras were turned off in 1990 after Voyager 1 took the famous pale blue dot photograph, that image of Earth as a tiny speck suspended in a beam of sunlight, captured from a distance of about 4 billion miles. Carl Sagan, who championed the photograph, wrote that the image underscored the responsibility to deal more kindly with one another and to preserve the pale blue dot, the only home we have ever known. The cameras were shut down because the power they consumed was needed for instruments that could still do science. The Voyagers stopped looking back. They could only look forward, into a darkness that would never end. When the last instrument on each spacecraft finally loses power, sometime in the early 2030s if the Big Bang maneuver succeeds, or sooner if it does not, the Voyagers will become inert. They will carry no active electronics. They will emit no signals. They will detect nothing. They will simply drift. Two small machines, each roughly the size and weight of a compact car, tumbling slowly through the interstellar medium at speeds imperceptible on any human timescale relative to the distances involved. At their current velocities, the Voyagers will not approach another star for tens of thousands of years. Voyager 1 is headed in the general direction of the constellation Ophiuchus. In roughly 40,000 years, it will pass within about 1.7 light-years of a star called AC+, 793888, in the constellation Camelopardalis. It will not be close enough to be captured by that star's gravity. It will simply drift past, unnoticed, undetected, carrying its golden record through the void. The golden records themselves are perhaps the most poignant artifacts humanity has ever created. Each is a 12-inch gold-plated copper disc, encoded with 116 images, greetings in 55 languages, a selection of natural sounds including wind, thunder and birdsong, and 90 minutes of music ranging from Bach to Chuck Berry to Navajo chants. The records were designed by a committee, chaired by Carl Sagan, intended as a message to any extraterrestrial intelligence that might encounter the spacecraft millions or billions of years from now. The cover of each record includes symbolic instructions for playing it, along with a pulsar map that encodes the position of our Sun relative to 14 pulsars, a kind of cosmic return address. The probability that any intelligence will ever find these records is vanishingly small. Interstellar space is vast beyond comprehension, and the Voyagers are tiny. They will drift for timescales that dwarf the entire history of life on Earth without encountering anything. The golden records were never really meant for aliens. They were meant for us. They were a statement about what kind of civilization we aspired to be. A civilization that explores. A civilization that reaches outward. A civilization that sends not just instruments but music and images and greetings. Because the act of reaching is itself the message. And that is what makes the absence of Voyager 3 so resonant. It is not just a missing line item in a budget. It is a question about identity. What kind of civilization launches two of the most extraordinary machines ever built, watches them succeed beyond all expectations, and then never builds another? What does it mean that the farthest things humanity has ever sent into the universe are artifacts of the 1970s, designed with less computing power than a modern thermostat, launched on rockets that no longer exist, powered by an isotope that we stopped producing for decades? What does it say about us? That our most distant ambassadors are slowly dying in interstellar space, and we have no replacements in flight, in production, or even in approved development. These are not comfortable questions. They do not have clean answers. The people who work in planetary science and heliophysics are deeply aware of what has been lost, and many of them have spent their careers fighting to recover it. The scientists who proposed the Interstellar probe mission did so because they understand that Voyager's measurements of interstellar space are incomplete, that the instruments are aging, that the power is running out, and that once both Voyagers fall silent, humanity will have no presence whatsoever beyond the heliosphere. We will have retreated, not by choice but by default, from the farthest frontier we ever reached. And the gap between Voyager's last transmission and the arrival of any successor probe could span decades or more, a period during which the only region of interstellar space accessible to human study will go completely unobserved. That gap is not inevitable. It is a choice, or rather, it is the absence of a choice. It is what happens when a civilization does not actively decide to sustain its most ambitious explorations. The momentum does not maintain itself. The funding does not appear automatically. The political will does not persist without advocates. The engineering expertise does not transfer itself across generations without deliberate effort. Everything that made Voyager possible required human beings to fight for it, to argue for it, to build it against institutional resistance and budget constraints and political indifference. And when those human beings retired or moved on, and when no equivalent cohort replaced them with equivalent leverage, the momentum dissipated. Voyager 1 and Voyager 2 are still travelling outward tonight. They are farther from home than any object humanity has ever made. They are carrying recordings of music and greetings from a world they left behind nearly half a century ago. Their power is fading. Their instruments are shutting down one by one. Their whispered signals take nearly a full day to reach the antennas that still listen for them in the California desert and in Madrid and in Canberra. And behind them, in the direction of the pale blue dot they photographed 36 years ago, there is nothing following. No successor, no heir, no next step outward, just the expanding distance between two aging machines and the civilization that built them. A distance that grows by 20 miles every second, in silence, in the dark, with no one coming after. The real reason there was no Voyager 3 is not that scientists lacked ideas. It is not that the technology was impossible. It is not that the destinations were uninteresting. It is that Voyager emerged from a moment when opportunity, ambition, institutional will, and a once-in-a-lifetime planetary alignment all converged in a combination so rare and so fragile that it could not sustain itself beyond the missions it produced. That moment was not the beginning of a new era of deep space exploration. It was the era, brief, brilliant, unrepeated. And the hardest thing to accept is not that the window closed. It is that we watched it close, year by year, budget by budget, instrument by instrument, and did not open another one. Somewhere out there, past the heliopause, past the bow shock, Past every boundary that separates the familiar from the unknown, Voyager 1 is still moving, still carrying its golden record, still drifting outward through the space between the stars at 38,000 miles per hour. It does not know that nothing is following. It does not know that the civilization which built it chose other priorities. It does not know that the question of its successor remains unanswered after nearly 50 years. It simply travels, outward, alone, into a darkness that has no end. And back on Earth, the antennas still listen, the engineers still calculate, the scientists still propose, and the question still hangs in the silence between the stars, unanswered, uncomfortable, and more urgent with every passing year. Why have we not sent Voyager 3 yet? Maybe the better question is whether we still remember how.